Good morning, ladies and gentlemen. My name is Ratna. I'm your moderator for the key session, now on the key principles of tropical architecture and engineering that will be presented by Dato Dr. Kenneth Yeang Kin Moon. Let me give you a little bit background of Dato Ken. Dato Dr. Ken Yeang is an architect and ecologist best known for his ecology-based signature architecture, distinctive verdant green aesthetic, and performance beyond green rating systems. Driven by a pioneering spirit, Dato Dr. Ken Yeang's long involvement with sustainable design began in 1971 with his research work on ecological design. For more than 40 years, through his commitment, he has developed ideas, principles, and systems in ecological and bioclimatic architecture, contributing to the advancement in this field as evident in his design, research, build work, and writings. He is a recipient of the Malaysian Institute of Architects Gold Medal, the Government of Malaysia's Merdeka Award, the Architectural Society of China's Liang Xicheng Award 2016, and many others. Without further ado, please let me invite Dr. Ken Yeang to give his presentation. Dato, are you ready?
I'm ready.
Great. The screen is yours, Dato.
Hello, everyone. This is the title given to me, Advances in Tropical Architecture. And my subtitle is From Bioclimatic Architecture to Ecological Architecture. And there is a logical progression for me. Now, tropical architecture is defined as bioclimatic design, means designing with climate. And this is the map of all the different climatic zones in the world. But if we just look at the tropical zone, but even within the tropical zone, there are subclimatic differences. Rainy tropical, wet and dry tropical, I can't read my own handwriting. Sandland tropical, hot and negligible, humid tropical, dry tropical, and humid and arid tropical. And so even within these zones, when you try and design with nature or try to design with the climate, there are subtle differences that we have to address. Now, the key design factors, these are some of them. There are many books written on this. The best are written by the OJ brothers, Victor and Alida, in the early 60s, Baruch Giovanni, and also in the mid 60s by Königsberger and people like that. But these are some of the key factors. When you design in tropics, you have to be very aware of the climatic data. You have to find out what is the acceptable level of comfort, because that varies from country to country and that varies from culture to culture. Some people can tolerate a higher level of heat than others, and other people becomes very sensitive. And then the orientation of the building is important, because if we look at the sun path, then that determines the orientation of building, and that what you want to do is to have minimum facades of your building facing the hot sides of the solar path. And then the building configuration is important, the shape of the building. And then the solar insulation, how do you keep that away, the thermal control and glare. And then use of wind. The use of wind and natural ventilation can contribute towards reducing the use of energy. And also the facade design. And of course, facade design includes aspects such as sun shading, and the type of glass that you use, and type of insulation. For instance, the low E glass is very effective, but expensive. And then the daylight penetration into the insides of the building is important. For instance, in Germany, no desk is allowed to be more than 7 meters away from a window, because that's the deepest in which daylight can penetrate in Germany. And then rainfall is important, because we need to not just collect the rainfall. At the moment, what happens with rainfall is that it falls on the ground, it goes on the impervious surfaces, goes to a drain, then it's gone forever. But in nature, the water that falls on the ground stays on the ground because it filters down into the groundwater. So we need to try and recycle and close the water cycle as much as we can. The humidity affects also our comfort, and then there are other factors. So these are some of the factors that we need to consider when we design in the tropics. But the best way we can learn actually by looking at traditional architecture, because the traditional architecture were designed by people through intuition, through trial and error. And so by doing so, you have an architecture which responds, to the climate. So for instance, if you take the typical Malay house, it has sloping roofs to keep out the rain. Then it has deep eaves to keep out the sun, and gives some protection. There's an air gap between the eaves and the walls for cross ventilation. The windows, if you look at the traditional Malay house, the layers of windows. You have the louver panels on the outside. You have the balustrade to stop you from falling out. The inside you have curtains, so you have a triple skin, facade. And then, of course, in the Malay house there are transitional areas like veranda ways in the traditional shop house. But in the Malay house, it's a Serambi because it not only serves as a semi-enclosed space, there's also a social zone for interacting with the rest of the people in the kampong. And then the floorboards in Malay house, it has gaps in between to let the wind through, and it's raised above ground to avoid heavy rain and from being having a floor being flooded, and also to keep away animals. And so what we need to do is to study our traditional architecture, find out what is it in it that we can reinterpret in contemporary times. And this is why tradition and culture is very important, so to go back and study it. And so this is just an example of analysis of the traditional Malay house, and that there are other house types that we can analyze. Now, as a case study, I want to show a project that we designed in Putrajaya. It's called the Swasana Putrajaya. And the first thing we do when we design is to see what, we do work all over the world, and that to find out what is the latitude that we're working in, because that gives an indication of the vegetation and gives an indication of the climate. So Putrajaya is about 2.9 degrees north of the equator, and that gives an indication that this is the tropical climate. Now, designing with climate gives us a climate responsive structure, which is an ideal armature for ecological architecture. This is a project we finished about 2 years ago. It is by the bridge, and it's along the route, along the boulevard, all the way to the Prime Minister's residence. And so it is in that little white square over there, and the Prime Minister's office is right at the end. And so you can see the building, which is there on the white squares by the bridge, and then it's along the boulevard to the Prime Minister's office. Now, it's also the wrong spelling mistake. It is two asymmetrical V-shaped towers, with the public realm in between. That is aligned with the Wawasan Dataran, and the axis goes all the way down to the Millennium Monument. So there you are. This is the axis from the Dataran down to Millennium Monument, which is also designed by us. And that's the bridge. And then that's the Putrajaya offices on the right-hand side. The two towers, the V-shaped towers, is the public realm, and this is the place where people can sit, people can have eat and drink. And on the ground floor, facing this public realm, restaurants and cafes, and that people can create a buzz around this locality. This axis, you can see the Dataran all the way down to the Millennium Monument at the end, and Millennium is right next to the Ministry of Finance, and other buildings in that vicinity. Now, we talked a lot about the climate, talk about tropics, but you cannot design the tropics without looking at the ecology and natural vegetation. So this is a different natural vegetation for within the ecological within the tropical zone, And that, it's quite clear that, this is the biodiversity diagram for a certain species of butterflies. And you find that near the equator is the highest level of biodiversity. And so we have to be very careful when we design in this locality, and that the further higher above the altitude, we don't have to be too concerned, although there are some areas which are extremely biodiverse and sensitive. But particularly in the tropics, we have to be very, very vigilant of what we do on the land. Now, when we design, the first thing we do is we create habitats within the development. Now, this is a unique way of development. Very few architects do this. A lot of architects put vegetation buildings, but they don't know why they do it. They just put, sometimes the vegetation they put into buildings are actually invasive species, which is not good for locality. But what we try to do is to create habitats on the ground, habitats in the air, habitats in the roof, habitats within the buildings. And so this is the first thing we do, is to create all the habitats we can within the development. And then we do what we call a biodiversity matrix. And so this matrix, we have the habitats on one axis. On the other axis, we start to look at the species that we want to bring back into the locality, which have been removed when they excavate the land, because by the time we got to the site, the land has been cleared. All we have is just the red soil. And so we try and choose the species or the habitats that will attract the fauna, the flora, that will attract the fauna that we want to bring back into the site. And so that is, I call this the biodiversity matrix approach. And then from there, we choose the flora that will attract the fauna. From there, we prepare the species, prepare the matrix, and see how they interact. How we can bring the fauna back for feeding, breeding, and refuge. For feeding, breeding, refuge, and for prey. And then once we set this together, the next will be then to try and design the landscape conditions within the site, so that then this becomes the whole building, the whole development becomes a total living system. So we call this a biodiversity approach to design, and that this is a method that we've developed to enhance the biodiversity of the location. Now, if you go back to the diagram I showed earlier on, reinterpreting the features from a traditional Malay house, deep eaves and shading to keep out the sun, air gap for cross ventilation, multi-layered windows for climatic control, louvers, balustrades. So with this project, the traditional approach to keeping out the sun is horizontal louvers. I thought, well, there must be alternative ways for doing this besides using louvers. So we thought maybe we should use fritted glass instead. So with this project, we use a glass which is fritted with a pattern on it. And for cultural reasons, we took the Songket pattern, and that with this pattern, 50% of the glass are fritted white patterns to keep out the sun. And then I have air gaps between the glass panels so that the wind can go through, and this is the outer skin. And then from there, you have an air gap. You can see on the right-hand side, it's like a walkway, and there is about a meter gap between the outer skin and inner skin. On the left-hand side is the fritted glass outer skin, in which 50% is clear and 50% is opaque. And you can see the Songket pattern. And then the view out from the passageway from the inside is the fritted glass pattern, and then a walkway you can see on the right-hand side in this space between the inner skin and the outer skin. We wanted to shape the building because this is an upmarket location, so we took the diamond as a metaphor for design, and so the building's shape is faceted, so that to look like a jewel. Now we wanted to check how effective is the fritted glass, and that the typical office building, the baseline building in Malaysia uses 210 kilowatt hours per square meter per annum. But for this, by using the fritted glass, we got it down to 136.18 kilowatt hours per square meter per annum. And so the fritted glass actually works, and it is a novel way of keeping out the sun and yet giving the building its own shape, its own form, without affecting the regularity of the internal spaces. So this is to show that it works. Now, the solar path is very important. In the equator, especially in Putrajaya, which is about 2.9 degrees, 3 degrees above the equator, the sun is almost east and west. The sun rises, as you know, in the east, goes on top overhead and goes to the west. And a third of the day, if you like, is in the east, a third of the day is above, a third of the day is on the west. So these are the areas where you need solar protection. But if you compare to the northern hemisphere, let's say like in Paris, which is 48 degrees north, the sun is very low. And on top of that, they have seasons. So you have to let the sun in. So it's a lot more complex to design in relation to the climate in the temperate zone and the cold zone than here in the tropics. Obviously, we only have more or less one consistent season throughout the whole year. But in Paris or in London or in Europe, you have in winter, you have spring, winter, and autumn and summer. You have two extreme seasons. You have cold season like winter, and you have the hot season, which is summer, and then you have the two very nice mid seasons, which is in spring and autumn. But the approach to the facade is very different because in the cold climate, you have to let in the sun in the winter because you want to get the warmth of the sun and get as much sun as possible. And the sun is very low. And so the type of louvers you have has to allow for the sun to come in. But in the summer, you reverse it because it's hot. Then, you have to keep out the sun. And so, in the cold climate and temperate climate, you have, the facades, which are operable. On top of that, the mid-seasons are good seasons. The mid-seasons are the seasons where you want to have as much natural ventilation as possible to try and extend the hot season and the cold season. So this is the climatic approach in the cold climate and in the temperate climate. Whereas in the tropics, it's much easier. We just have to deal with the eastern sun, the overhead sun in the midday, and the western sun. And so for the western sun, for instance, for this particular project, we angled the glass. So you can see that the facade is changed on the western side. You can see in the red line on the left-hand side, western glass. And so this is the western facade, and which is angled to keep out the sun from the insides of the building. And then these are different habitats that we have in the building. And then what we do is that we bring the habitats not just on the surface of the building, within the building, on the roofs of the building, on the walls of the building, but we bring it all the way down into the basement, which we call an eco cell. This is a master plan we did for the Hong Kong waterfront a few years back. And these are where the eco cells are. And this idea of the eco cell was developed when we worked on this project. It's basically a spiral ramp that brings the vegetation all the way down to the basement. And so the eco cell does 5 things. It brings vertical integration of the vegetation, provides opportunity for rainwater harvesting to close the loop. It provides an opportunity for natural ventilation to the insides of the building. It brings daylight into the insides of the building. And at the bottom is where we could have an ecological machine for treating the waste material, or we can have a biosphere. And so this is the eco cell device that we start to put into some of our buildings. And so for this building in Putrajaya, we have an eco cell, and this is the eco cell. The vegetation starts from the first floor, goes into this ramp, and you can see the planter on the left-hand side of the walkway that goes all the way down to the basement. Now, it's easy to put habitats on a medium-rise and a low-rise building or low-rise development. So how do you create habitats in a high-rise built form? Because you don't have very much land area. The floor plate is small. And so what we do is that we create habitats on the facade of the building, and we stratify it. So that means, we try and look into the ecology of the areas, near the site. So the site's that red dot, and look at the species within this area, and look at the species near to our site. And from there, we try and prepare again a biodiversity matrix for this project. And the idea was that try and have continuous vegetation going all the way up to the top. These are different patterns that guide our work. You either put all the vegetation in one location, you centralize it, like in a tower on the left-hand side or Central Park in New York, You have a spotty planting pattern, as you can see in the top, in the second diagram, which is like Georgian London, where you have a series of green squares. But in the building could be in a spotty relationship, or you can have a stepping stone. The green areas are fairly close to each other, so that like a stepping stone, vegetation, the species can move from one to the other. But the ideal one is the one on the right-hand side, in which all the vegetation is linked not just to the ground, but linked to the hinterland and to the basement. Because by doing this, you have a larger pool of resources in which a species can share. It enables species migration and movement within the vegetated areas, and it also engenders a much more stable and stable ecosystem habitat that can survive without human intervention. And so what we try to do then is to link the green areas in the ground. Because what human beings do is that when we go to any land, we fragment it, we chop it up, like cutting like converting a cow into a burger. And then we should try and link it. So if people ask me, what should we do with cities? We should link all the green areas in the city so that we have a greater connectivity and ecological nexus, but not just within the ground plane. We should try and connect it vertically as well. And so in this way, the whole city then becomes, not just abiotic, not just inorganic, but it should be linked as a continuous set of, you should repair the fragmentation that human beings have done to the locality. And so with this project, we stratified the habitats. So we try and design the lower floors for dragonfly. We choose a species that will attract dragonflies. And then after that, we call the butterfly zone, attract the butterflies. And then in between, we have what you call the songbird zone. And then the top one is for migratory birds. So this way, we stratify the habitats vertically. And so, with the idea in this project, which is one that we designed in Singapore, is to use a continuous vegetation that goes all the way around the building as a vegetated ramp. And so with this project, what we try to do is to have a continuous ramp of vegetation that flows all the way up to the top of the building. And this way, as you can see in the other diagram, you have continuous vegetation. And by doing this, you create a building which try and balances the biotic with the abiotic constituents to make it into a living system in as much as possible. Of course, this is easier said than done, because half the time I'm fighting with clients, and client says, "Oh, do you want to put veggies in your buildings? And it's going to cost me a bit more money. I'm not getting any profit out of it." And so you have to tell clients that designing a green building, designing a sustainable building, is not for commercial reasons. It's for ethical. It's the right thing to do. And so, of course, half the time I'm trying to persuade them to do it, and that is what we do all the time. But the whole idea of this building is that having continuous vegetation, then whenever the building, whenever there is an adjoining building next to it, then this is an idea that we could bridge across to the roofs of the next building. And then in this way, we colonize the whole city. The whole city then becomes a vegetated city, a green city, and the city where it's covered with biotic constituents instead of just being inorganic, as what most of the cities at the moment. So with this idea, this is a project we did in the One North district in Singapore, and it's in the Novena area. And here we brought the vegetation continuously in a link, in a spiral, going all the way out from the ground up to the top of the building. And so as you can see on the right-hand side, it's a continuous link vegetation. And above this is the idea that in master plans, you would have ecological corridors and ecological fingers that then converts the city, that balances the abiotic, the inorganic, aspects of city, and make it much more like an ecosystem. But by bringing vegetation into the city, and the more we put in, the more ecosystem services we bring back into the locality, which is good for the environment. And so this is the building where we had louvers on the outside. and then you can see the vegetation in a spiraling ramp going all the way up. But what we've done is they put a walkway next to it. So this walkway means that people can service the plants without going through the interior office spaces of the building. And so here it is, you can see, it being used, you can see the sun shading on top, you can see the plants and people actually using it. Then we said, well, we might as well make this into a park. So we call this a linear park. And that with every facade, we climb one floor. And so with, here this shows, how it climbs one. Here's the building in this context. And that you can see the ramp vegetation going all the way up the facade. And that with each floor, we cover one facade. And then you can see that here, this is a close-up of the ramp. You can see the walkway, you can see the vegetation, and that the facade on the left-hand side, and you can see sun shading. And of course, the plants help cool the building. It keeps, because it gives out, a certain amount of oxygen, which then gives the lower microclimate. It makes it cooler, and that is also a healthy environment for the locality. And so the vegetation starts on the ground, climbs up to the building, right to the top. And then actually, if you stretch this ramp, this vegetated ramp out, it's about 1.3 kilometers long. And if you look at the green, vegetation put in, it is 12 times more than what it is required for certification for the green mark. So you can see that we try and bring as much green as possible into the building of this project. And then now, it's deadly boring if it's just a ramp going up. So what we do is that whenever the ramp hits a corner, it opens out into what we call a sky core. So these are places where it punctuates the ramp. And so that these are spaces where people can, well, the sky core, so you can see at the corners down here. These are spaces where people can go out, they can, have a meal or have a cup of coffee or, smoke a cigarette if they wanted to. And so these are the sky courts. On the right-hand side is the project that we're working on in London, where we have sky courts, staggered all the way up to the top of the building. But on the left-hand side is the detail, is a photograph, image of one of the sky courts in this project. And here's a bigger one, which is at the corner. And this is the view from the side. But more than just the sky courts, halfway up the building, I have a roof garden. And so this is you can see the roof garden, the steps all the way up, and then another roof garden at the final top floor. And these are where the roof garden is. You can see in this plan, and you can see the series of roof gardens. The building was finished about 8 years ago. And this is the mid-level roof garden. And this is the uppermost roof garden at the top of the building. Now, the requirement in Singapore to get the certification is, they call the green mark. And I have to get at least 6 points for this greening area. But for this project, we've got 12.2, so we got twice what is required. So the certification system, whether it is a green mark, LEED, or GBI in Malaysia, it's only a guide. It doesn't mean that, we fulfill it and that's it. We just have to double it, exceed as much as we can, which is better for the environment. Now, if you look at the building, it looks like a building, but actually it's just 2 blocks, which is wrapped by a wrap facade. In between the 2 blocks is an atrium. And the atrium opens up to the sky. You can see operable glass louvers on top. But these louvers are open most of the daytime so that the space in this atrium is not air conditioned. Now, just as some cold air blowing in, so that I have some air going into this space, but it's not fully air conditioned. It's what I call a mixed mode space, and that the glass louvers are open most of the time, but if it rains, it automatically closes, and so it closes just like this. And so in this way, I have, it's an operable system for the building. You can see on the right-hand side of the glass roof is the mid-level garden, and then the roof gardens above. But between the 2 blocks, I have a bridge, and so I have a bridge that links the 2 blocks. And so this is the bridge. You can see the bridge there, and this is the bridge that links the 2 blocks together. Now, we also use this project as an opportunity to experiment. Now, most light shafts that goes, most air wells that link the buildings are vertical. But for this particular project, we said, why don't we have a diagonal light shaft? In this way, we bring light, right all the way down into the insides of the building, and that when people walk past the street, they look up, they can see the insides of the building. So this was an idea we had. We call this a diagonal light shaft, and that it's just a small square. It's not a huge light shaft. It cuts at the diagonal going all the way down, and on top of it, it have a big opening which opens out into the atrium. And so this is the view from the street, looking up the light shaft. You can see, all the terraces along the light shaft, and then on the top of that, you can see the glass of operable glass roof. And then this is another view looking up. You can see it looking up from the bottom, and then this is the view looking down. Right, you can so for people from the offices, they can actually see the street from this level, and from the street you can look up. You can see the insides of the atrium. This is a simulation of the daylight penetration into the floor, and it's what it means is that I have my floor plates are too deep. That means that the blue areas means they don't get hardly enough sun. And so I should have really shaped the building so that glass to glass, it should be not more than 15 meters, whereas I have more than 20, 30 meters from glass to glass in this particular project. But it's just to show that you cannot be perfect in everything. But this shows that I got as much glass heat, I got as much light as I can into the building. The diagonal light shaft works to some extent, but it is still actually very dark with the insides of the building. So then, so this is where the light shaft is. And then again, the vegetation goes all the way down to the ground floor, and it goes all the way down to the basement. I call this an eco cell. And so this is where it is located on the ground floor plan. And then the eco cell brings vegetation, brings daylight, brings water, brings rainwater, and this is the eco cell going around the basement. And the basement I have a tank which collects the harvested rainwater. So now I'm going to end in a minute. Ecological design is basically a biointegration of these four factors: of nature, of our human society, of technology, and water. With nature, we have to understand that there are ecosystems that we need to preserve, we need to be sensitive, and there are species that we need to relate to and that we need to protect. And then human society is not just community, but our entire system, our social, economic, political, education, institutional system, all have to change if we have to have a sustainable future. Now, there's a tall order. I can't do this in my lifetime. I don't even have the ability to do it. But people have to recognize that our economies have to change. We have to change our lifestyles. We cannot have a way of life in which we want more and more and more different things. We cannot have a diet where we eat, meat and all the time. We should have a diet which, get our proteins from somewhere other way. Our education system means we have to teach ecology and natural history to people from the time they were children, so that they understand that everything that they do has an impact on the environment. Just flipping a switch at home has an impact on the environment. And then, so there's economics have to change. We have to have a circular economy. Then our businesses have to change, because the businesses and the industries have to stop becoming throughput. Throughput means you take something, take energy, use it, and then when you finish it, you throw it away. We should need to close the cycle. We should, have a cyclic system of economy and our way of life. And our government is the most powerful entity in our societies. The government can effect the change. But what happens if the government doesn't want to change? The government, treats it as, second priority, or second government negates it as President Trump in the U.S. And then we're all in trouble, because, then we have to tolerate, a devastating environment for the several years that the person becomes, president of the country. And so our social systems, our economic systems, our industrial systems, our political systems, our education system, and our institutions have to change. Then the built environment is everything that we make as human beings. It's not just buildings, but it includes the toys, the clothing, the kitchenware and everything. it has to be part of this cyclic process, and that recycling and reusing. And at the end of the day, when you cannot recycle and reuse it anymore, we have to reintegrate it back into the environment. And so the whole system of use and flow of material in our human society or in our built environment has to be rethought out. And then, of course, there's water. Water is what life is all about. You know, when astronomers look into the sky, look into the Mars, look into the planets, the first thing to look at is their signs of water, because if there's signs of water, means there is organic life. And so water is what life is about. And we need to close the loop as much as possible. What is happening now is that when we go on, human beings go on a piece of land, we fragment the land. We chop out the land, we separate the land with drains, with roads, with fences, with impervious surfaces. And so that, you know, the species then becomes fragmented. Once it becomes fragmented, the survivability is reduced. And that, you know, what we need to do is reconnect the city, make the city whole again. So, and what happened is that the rainwater that falls on the land in nature, falls on land, goes back into the ground. But right now, what happens is that the water that falls into the land, into the impervious surfaces, goes to the drains into rivers, into the sea, and is gone forever. So we should try and retain and recharge the groundwater as much as we can and close the cycle. So in our built environment, we should try and reuse water. We should try and treat them and try and use it for, if we cannot use it for potable purposes, we use it for cleaning, for other purposes, for irrigation. And so these are the key factors in designing an ecological architecture. You have to integrate nature, humans, technology, and water together. These are different factors we have to take into consideration. I will expand it a little bit. But this is the diagram that drives our work. You know, we look at, you know, these 4 factors in every project and see how we can integrate it as much as we can. But of course, this is easier said than done. It's a very difficult task, and to be frank with you, it's a miserable life being an architect. And so this is what I've been asked to talk about, advances in tropical architecture. And really what I'm talking about is that tropical architecture is designed with climate, and the Olje brothers called it bioclimatic architecture. But we have to move from bioclimatic architecture to ecological architecture, because even though we start from bioclimatic architecture, which becomes an armature for ecological architecture, we have to advance. We have to move from just designing climate to design with nature. And so that's the end of my talk.
All right. Thank you, Dato. Thank you for interesting presentation on the current advancements in bioclimatic design field to suit the hot tropical climate and humidity. Let's move on to the question and answer session. The first question is, how far and to what extent has the construction sector in Malaysia, especially architectural designs, have adopted these bioclimatic designs?
Well, a bioclimatic design is designed with climate. So, you know, I would say a large percentage of architects design with climate. They realize that the all glass, totally air-conditioned building is not good for the environment. We try and design buildings, the facade which have sun shading. We try and design buildings which are less dependent and reduces the energy consumption. The trend now is to do what we call NZEB, which is net zero energy building. So design buildings which is net zero in as much as possible. And so I would say a lot of architects do that. A lot of architects are already doing it. But we have to move from bioclimatic design to ecological design. And so that is the next move, and that is the next generation, if you like. But to be frank with you, I've given up on my generation, because most of the architects in my generation were not brought up in ecology. You know, they all say we do sustainable buildings, but actually do sustainable buildings which are very engineering driven. My hope is that the next generation of architects will learn ecology and they will apply it to the work. So this is how I see the future for architecture in this country.
Great. Okay, shall we go on with the next question?
Sure.
Okay, is it possible to develop sustainable environment-friendly construction with the concept of smart city? If possible, what are the factors that should be taken into consideration?
Well, actually, ecological design is smart city because you have to monitor the environment. You have to know what are the changes. For instance, vegetation can sequester pollution. Vegetation inside the building can enhance indoor quality. But the extent in which it works, eventually it sequesters, eventually it works, is through smart systems. And that smart systems means that once we monitor, we we're alerted, then we take immediate action. And so sustainable design is really very tight and very closely tied to smart systems. But we're not using it the same way because we're just using smart systems for cars, for transport, for all sorts of things, for exchange of information, for data, for use of big data. And so we should apply the ecology, apply it to the sustainable systems, to energy, to water, to environment, to indoor air quality, and to external environment, and to the provision of ecosystem services. This is what we should be using smart systems for, but nobody's doing it. That is the saddest thing. Although I have, I'm not saying that's not true, so nobody's doing it. I have some friends in Hong Kong and the US who are doing it. But those of us who will try and design ecological buildings and related to climate, related to the conditions outside, and using smart systems, few and far between.
Thank you, Dr. So the next question will be, what is the most effective way to enhance building designs towards achieving high or sustainable energy efficiency?
Well, okay, let me just go back a few steps because designing isn't just about energy. Design isn't about ecology. To me, a good design has to do four things. First of all, it must work. That means, the circulation is right, everything, functions well. Because if a building does not work, if it's not functional, then it's a useless chunk of masonry, useless chunk of inorganic stuff. And so the first criteria for me for good design is that it must work. The second is that it must be beautiful. I mean, that's subjective, of course, but that's why we're architects, because we try and design things which are as beautiful and try and make it as beautiful as we can. Can you imagine, living in a building which looks like a prison, or which looks, godforsakenly ugly? And so, beauty is very important, aesthetics is very important. The third is obviously the building must be built high quality, must be within cost, must meet government requirements, and so must be green, it must be low energy. So being low energy is just one criteria of a whole series of criteria. But the fourth criteria is the most important one. It must make people happy. Can you imagine design building, it looks beautiful, it works, and it meets criteria, but people are incredibly unhappy living there, unhappy using it. And so, when we start designing, we don't just look at it green, because we're designing green buildings as second nature, ready, meeting authority requirements, designing a high quality building within cost. It should be second nature to anybody who's an architect. But the biggest issue is that we look at the project and we ask ourselves, what can we do here that will make people happy? What can we do here that make the users happy? What can we do with the house that make the family happy? And if we're able to achieve this, then our whole raison d'etre, the whole reason why we're architects, is justified. And so these are the criteria. So now talking about energy, what we need to do is to look at the baseline energy requirements of the building. Let's say a typical house uses about 40 to 60 kilowatt hours per square meter per annum. Can we reduce this? Can we, let's say, design it so with the walls have insulation so that it stops the heat from coming in. It's naturally ventilated so that the whole house is cool, and that the roof is insulated, and that we use as much renewable energy as we can. We use photovoltaics on the roof, or use hot water solar collectors, and if possible, we use wind energy. The wind energy is extremely difficult in Malaysia because most of our urban areas, we have very little wind. Now, for wind energy to be effective, you have to be outside in the countryside, And have to get at least, wind generators must generate at least the wind speeds of at least over 5 meters per second. Extremely difficult, over 5 meters per second. Even where I am outside in Taman Sri, UK, I only get wind, in the late evening, but air is really still in the daytime. And so, using renewable energy then has to depend on photovoltaics. Now, the next generation of photovoltaics is to see whether we can, not generate electricity, energy direct from the sun. And so there are many experiments going on at the moment. There are systems what you call the dye cell, which using a dye to convert solar energy into the sun into energy. But it's a long way to go. But even so, with photovoltaics, when I started practice maybe about 30, 40 years ago, the efficiency is very low. It's only about 6%, 8%. But now the efficiency of photovoltaics has gone up to about 15 to even 20%. And so, technology actually makes up for a lot of advancements. And so when you start designing a building, let me just summarize very quickly. We ask ourselves, what can we do here to make people happy? Is it the space? Is it opportunities to do the activities they want, whether it's hobbies, whether it's cooking, whether it's entertainment, or whether it is outside living, whether it's sports or eating healthy. So we ask how we can make people happy. Next, we look into how we can balance the biotic components with the abiotic components. We try and bring as much vegetation in so that the house itself becomes not just 100% inorganic, which is most houses at the moment, but we try and make the house a complement of biotic constituents of vegetation so that it becomes a living system. And we try and produce ecosystem services within the built environment so much as we can. So next, then we can say, look, we're having sought out the energy equation, and then we try and that the house is a low energy building. Then we see how we can make the house into a net zero energy. That means we are totally not dependent on non-renewable sources of energy, like coal or oil or some sort of non-recyclable material source of energy, but try and use photovoltaics, use wind, and if it's by the sea, we should try and use tidal energy if we can, and that. So that is the next stage. But in between full mode, which is which is a building which uses 100% technology, air conditioning, and passive mode, which is what design new climate, which is what tropical architecture is about. There's a transition area which I call mixed mode. Mixed mode means it's not 100% no technical systems, as in let's say the bioclimatic design of Malay house. On the far end is the building which is a built system which is totally dependent on air conditioning. But in between is what they call mixed mode, where those areas that doesn't need to be 100% air conditioned, we can use cooling systems. We can use ceiling fans. We can use exhaust fans. And so, for instance, one project we did a shopping mall, which is in Taman Tun. Instead of air conditioning all the retail areas, we have 3 extractor fans over the canopy, which sucks the air out from the area, and so this lowers the temperature. Now, this, the comfort level that we should try and achieve with air-conditioned room is about 23 degrees. But using the systems, it's totally impossible to get 23 degrees unless it's fully air-conditioned. So we try and get as close to 23, maybe 27, 28 degrees. So we have to accept that it's going to be a little bit hotter. It won't be 100%, equivalent to what you're used to. But I call this mixed mode. That means some mechanical system, like ceiling fans or extractor fans. And so these are some techniques we use to try and lower the energy consumption in the building. But there are other things like materials. We can try and use recycled materials as much as we can. We should try and standardize so that we don't have to have so many customized items. But it is a holistic thing. It's not just building. Our lifestyles have to change. I don't know how many pairs of shoes you've got and how many pairs of dresses you've got, how many pairs of jackets. I've only got 5 pairs of shirts, 6 pairs of socks, 7 handkerchiefs, and that's it. and I don't need to have any more shirts. I don't have to have any more shoes, although the marketing and advertising encourage you to buy more and more and more and more and more. We don't need more and more. We just need a visceral and simple life. And same thing with food at the same, as well. And so our lifestyles have to change.
Sure.
So that's the second. That's all my thoughts.
Great, great. Thank you, Dato. The next question we have is, what are the obstacles in adopting bioclimatic design? Would you agree that the cost and lack of expertise to be the hindering achievements in this area? This is a question from Ms. Chang Sound Fong.
Well, bioclimatic design is easier in the tropics than in the temperate zone. Most architect friends of mine know how to do it. Not only that, they do it intuitively, and most of them are even taught how to do it at school. And so most of the schools of architecture in Malaysia actually teach design with climate, which is a very good thing. Now, getting it to the next level of ecological design, then that is the challenge. The biggest challenge, of course, is cost. Now, in the East, in Asia, people want things to be fast, they want things to be cheap. Whereas in the developed countries, people are a lot more sensitive to the need to design for a sustainable future, so they put a little bit more money into it. To me, when I design for somebody, or design for any client, we start with a budget because money is very important because, we're looking after the client's money. We usually ask for a percentage above the budget, between 10 to 25% for sustainable, to make the building sustainable. Now, for instance, the Solaris building in Singapore, the one with the ramp that goes all the way up, we got Green Mark Platinum, which is the highest rating you can get in Singapore for green buildings. That's 6.5% over industry's budget, construction cost for that building. Not 25%, not 10%, but 6.5%. But the energy and water savings amortizes the increased cost over a period of 8 years. And so over 8 years, the increase in budget of about 6.5% is amortized. But after that period of time, 8 years, it continues to save energy and water. And so the biggest justification for green buildings is that it saves energy and water. And so that is the best selling point for buildings. Now for the Solaris building, we save 70 cents US per square foot per annum. And so that's a lot of dosh, so you can actually justify green buildings by the energy and water savings.
What about the expertise?
Expertise for designing, let me go back. Designing, bioclimatic design, it is there. Every architect knows how to do this. What we have in Malaysia is a certification system, a green certification system called the GBI, which is nothing wrong with it. I think it's wonderful. It is one of the most engineering driven, and that most architects are able to fulfill it, able to achieve it. But we must go more than just that. We must look into green design, not just in terms of engineering, but also in terms of ecology. That is the biggest problem because my generation have not been brought up in ecology. I hope the next generation will be, and that is my expectation for the future. I'm an internal optimist, so I think that hopefully things will happen in the next 5 to 10 years. Now you have to bear in mind that I started designing ecological buildings back in 1971, and it was extremely difficult, when I started practice to try and get clients to build green buildings. So the easiest way I can get them to accept green buildings is like to start going back to bioclimatic design. But it wasn't until the 90s that people just suddenly all jumped up and says, oh, we have to do something about the environment. Then the engineers got into sustainable design. And that's when we had greater support and more people started doing work in it. The the green building rating systems started to become popular. And so from 90s onwards, I think things change. And so it's very optimistic for me because when I first started practice back in 76, 77, it was dismal. I thought, oh dear, I'll never do anything that will contribute to the environment, except perhaps designing bioclimatic low energy buildings. But if you fast, 20 years after that, people became, very committed to green buildings. A lot of architects are, but I hope that within the next 10 years or so, architects then move on to design ecological buildings, and that this will happen in the future before I start pushing daisies.
Okay, Dato, how do you integrate bioclimatic design to areas which are gazetted, such as the national heritage areas around Masjid Jami, for example?
Well, working with existing buildings is extremely difficult because you have existing structure to work with. And on top of that, a lot depends on the budget. Green buildings, I mean, it's sad but true, it's easier to be done with buildings with a medium to high budget. But if you're designing low-cost buildings, affordable buildings, it's extremely difficult to do totally green design. You can do as much as you can to reduce energy consumption, to make it comfortable without using too much, without using air conditioning or constantly using with some minimal mix mode. But you need a budget to do this. And so, how to answer your question? You have to do with what you can. On top of that, we have clients which are difficult. In Malaysia, we're a developing country. Doing things fast, doing things cheap, is important for a lot of developers. And when you want things fast, it cannot be cheap. When you want to be cheap, can it be good?
Yeah, you got to compliment each other.
So you have to tolerate.
Okay, I move on. What are your suggestions to address the deterioration of urban environment due to urban heat island phenomenon?
This is what Singapore is doing. You just put more plants into the city, because plants absorb, a lot of the heat. Plants with a large leaf index, and this is what Singapore is doing. It is putting more vegetation, and you plant more trees, and you put more vegetation in buildings. By doing this, it reduces the heat island effect. Heat island effect, comes about because of the heat absorbed by the inorganic surfaces, the inorganic mass. But if you have more plants, then the plants counteract the absorption of the heat by the inorganic mass, and then by giving up oxygen, it lowers the ambient temperature of locality. And so we should have more plants in our cities.
Okay, Dato. In your views, Dato, what do you think about our Malaysian architectural spaces that would change after COVID-19, in your views?
Well, COVID-19 means that the world, our environment, our city, our way of life will never be the same again. So it is, those people who think that we have to go back to the normal way of doing things, then it's a dream. We have to live with it. But that means, but COVID will not be with us forever. COVID came suddenly, and it's been predicted that COVID, will suddenly go away as well. And so, before the end of the year, COVID will go away. That means a lot of people are tempted to go back to the way of life they had before. And so it may change to some extent. For those who are conscious of it, then it means that we cannot design spaces which are compact. We have design spaces, public spaces and private spaces and semi-public spaces, which are a little bit more spacious, and that we have to have systems that will check how people use buildings, how people enter buildings, how people enter shops, and how people leave shops, so that they don't. Even though COVID has been with us, it will not go away in entirety, and so the danger of coming back again is there, and so we have to rethink the way we design offices, we design arrange furniture, we design restaurants. If you go to a restaurant now, it's only about what, let about 50%, 30 to 50% into the restaurant. And then you have these tables where you have crosses all over it, where you cannot see it. It's like pin checkers. And well, the arrangement of seats and furniture in restaurants will change, and COVID will come back again. And it's been predicted that even though in this period, COVID will come back maybe for a second round, and then it will go away. But it's been predicted that in 10 years' time, it will come back again. And so we have to anticipate this. We have to prepare for it, not just in our homes, in our cities, in our restaurants, in our public areas, but also in our hospitals. All the equipment, the PPE should be there, so that just in case it comes back again, we are ready. We're going to fight this in any way that we can. And so, but one of the things that is important to recognize that as an ecologist, you know that everything's connected. We cannot say, oh, this part of the country where we open up, this part of the country we lock down. All the country, all the environment is connected. We cannot do this. We cannot segment the lockdown and the open. So there's what we're doing in the US, which is pretty silly. That means it's like cutting your nose to spite your face. You never get rid of it. Either the whole country is coordinated and you stop people from coming for a short period of time, you lock down everybody for a short period of time because it's good for everybody. Otherwise, the whole idea of opening a little bit here, a little bit there, it's totally crazy. And so, but in the long term, predictions say that COVID will not, even though the virus will be inside, will be in our human beings, it will go away as fast as it came. But let's say it came, let's say in February or March. By if you see the projections, they say by I don't know whether it's true or not, but they say that by July the 8th, the Malaysia will be 100% safe. So, but let's give it a 20-30% anticipation. Let's say by August everything be fine, provided the second wave doesn't come back again. But so that means a lot of people after July and August we go back to to try as much normality as we can. But it'll never be normal. You have to rethink everything. You still have to check temperatures, and you have to give and that although the rebellious people in our community will fight it, will not accept it. But that's how it is with society. Can everybody do things the way you want it to be done? But it's predicted that within 10 years' time, it will come back again. And so we will anticipate it.
Okay, Dato. Next question. How far has the wood-based industries are producing materials from renewable resources such as bamboo, forest-planted wood? Is the gap between materials production and architecture design? Is there any gap?
I was reminded the other day, that Swedish girl called Greta Thunberg. You know who she is, right? She's the one who says, how dare you, you ruin my future. And so she made that declaration that the Chinese should stop eating with chopsticks because chopsticks are made from trees. So the Chinese government replied and says, well, chopstick is made from bamboo, and bamboo is a fast-growing plant, and it's not even a tree, it is a grass. And they counteracted by saying you should stop wiping your ass with toilet paper because toilet paper is made from trees. So anyway, how far it is, I think we should try and use renewable resources as much as possible. Nothing wrong with using bamboo, but we have to start designing with bamboo in a much more intelligent and inventive way, rather than doing buildings which are curved bamboo. Because studies have shown that it is possible to do high-rise buildings of 10, 20 stories out of wood. The biggest problem with using wood for doing design for buildings is a fire, and that you have to make sure the wood does not burn. That's the combustibility effect is there. but it is possible. They've done very large buildings in Singapore out of wood, so that in Japan and in some of the Scandinavian countries, they've done 10, 20-story buildings out of wood. And so it is possible to use wood, but make sure that it's not hardwood, because hardwood takes hundreds of years to grow. And once you chop down a tree, it's gone forever. So that wood, once you use it in the building, like any other material, if you use, let's say, aluminum building, you can recycle easily, you can melt it and use it again. But wood, when you can't recycle it, you have to either make that into wood chip, or you have to downgrade its use, because you already cut the wood and you can't use it again. And so we have to make sure it is used, what you call FS, forest certified, timber, and you also use timber which is renewable and timber which is recyclable. But nothing wrong with doing that. I have a friend, in Philippines. His name is Bobby Manosa, and he passed away about 9 months ago. He did a whole palace for Madame Marcos. He called it the Bamboo Palace, made out of bamboo. And I go visit his house in Manila. The whole house is made from bamboo. It's incredible. So bamboo is actually a very versatile material that we try and use.
Great, Dato. We have one question from Professor Fang Siu Moy. She's a fellow of ASM. She's interested to know whether the principles of feng shui applicable for designing sustainable buildings.
It's like I get asked all the time. You have to understand feng shui. There are many schools of feng shui. Now, if you're a scientist, the approach that a scientist has towards their work is what they call the hypothetical deductive method. That means you experiment, then a certain amount of experiments fail to success, then you move the knowledge forward and forward and forward. But the Chinese never never understood the hypothetical deductive method. So even though feng shui is one of the most logical, ecological approaches to doing design, they reached a level where they could not push it forward. And so what did they do? Feng shui then became astrological. And so there are many schools of feng shui. The astrological schools, have serious doubts about it, but the morphological schools of feng shui, a lot of it makes sense. Like, how you build by the waterfront, by the rivers, how you build in the hills, how you should face a certain direction. Like in China, the building should face south, obviously, because the sun comes from the south, and the cold winds from the north. And so feng shui, the morphological school, has a lot of sense in it, but it is the astrological school which baffles me. And I said, look, when it becomes astrological, then it's a lot of hocus pocus, which I don't believe, which then doesn't make sense to me. So feng shui does a lot of sense. Now, obviously, it's not just with the siting of buildings, not just to do with the shape of buildings. It also has to do with the furniture, how you lay out the furniture in your house. The other day I went to, this is really funny, because I went to my one of my specialist doctor, and I looked at his office, and I said, excuse me, doc, your reception counter is in the wrong position. The way it's designed means that the money will come into your business, it'll go up very quickly. And so, as I was saying this, his staff was smiling, says, you're nodding your head. Yeah, it's true. But the doctor said to me, hang about, I'm a Christian, they're talking total nonsense and I don't believe it. So there you go.
Yeah. Okay. Dato, the last question. How do we preserve the Malaysian architectural identity?
What is identity? So we should not be too concerned with identity. We should do it in a natural way. But to me, there are 5 ways of designing with culture. I'd call it design with culture rather than designing with identity. The first approach, but I call this situationalist. There are 5 ways of doing it, but you have to adopt the approach appropriate to the task at hand. It's not one size fits all, but you have to get the right approach for the particular task, location, the project at hand. The first approach is what I call replication. You replicate the traditional architecture. Nothing wrong with doing that. Yes. But for instance, let's say if you're designing a building in the Forbidden Palace in Beijing, you don't want to put a modern building. That's a total travesty. So you have to replicate the traditional architecture as much as you can. So in certain instances, in certain locations, you have to, the first strategy is replication. The second strategy is what I showed in my lecture, which is called reinterpretation. You learn from the tradition, you learn from the culture, you learn from the past, you learn from existing, from traditional architecture, and then you ask yourself, how can I reinterpret this in contemporary conditions, contemporary situations, in a creative and innovative way? So the second approach is what I call reinterpretation. The third approach is what I call genius loci. It means look at the spirit of the place. I mean, don't spirit not in terms of ghosts, but in terms of what is the feeling? What is the feeling about the place? For instance, if you know, I don't know whether you're born in a kampong or you're an urban lady, but if you live in a kampong, you know that there's a certain organization, a certain relationship between families, a certain relationship people, you know, that makes it unique. That is the spirit of kampong. Now, if we're able to reproduce the spirit in a contemporary situation, then we've done something. We have, you know, we have adopted, you know, the culture of and try to reproduce this in the contemporary time. So that's the third strategy. Fourth is what I call abstraction. That means you take an abstract object and you replicate it. You know, I have a friend, you know, very famous Malay architect. Hijaz Kasturi. He designed, you know, when he designed the land banking building, you know, back in the early 80s, he said it looks like the Chris Tumming, the Chris of Hang Tuah. There's a lot of speculation there, but that's his explanation. It's an abstraction of the Chris reinterpreted in a building form. And so, so the fourth strategy is abstraction. The last strategy is what I call neutrality. Neutrality because when I did the National Library in Singapore, I told the client to free the ground floor totally of any retail, any business areas. And so 80% of the ground floor is free for cultural activities. Why? Because culture is what makes a building unique. But culture changes all the time, and you have different cultures throughout the whole year. So I said, program activities over this space, that over the festival days, where Hari Raya, New Year, Christmas, or Taipazan, and have cultural activities that take place there. Because if you facilitate cultural activities there in a neutral space, the building becomes a cultural building. And so in this way, the 5 strategies, replication, reinterpretation, genius loci, abstraction, neutrality, are the basic strategies for design culture. But you cannot use one for all situations. You have to use the right one for the right place at the right time. IBM calls it situational approach, towards leadership. Well, that's a situational approach to leadership. I call the situationalist approach to designing with culture.
Thank you. Interesting insights. Thank you, Dato. Thank you for your presentation. Thank you for your time.
You're welcome.